Download this code from codegive.com, link in the description below. Creating a GPT, generative pre-trained transformer, model from scratch is a complex process that involves understanding deep learning, natural language processing, NLP, and the architecture of transformer models. In this tutorial, we'll outline the high-level steps necessary to create a simplified version of a GPT-like model using Python and PyTorch. This will be a conceptual overview, and we will include code examples where applicable. Part 1, Overview of High-Level Steps. 1. Understanding the transformer architecture. Learn about the architecture of transformers, which includes self-attention mechanisms, feed-forward neural networks, and positional encoding. Familiarize yourself with the components of a transformer, encoder and decoder, although GPT primarily relies on the decoder stack. 2. Setting up the environment. Install necessary libraries, PyTorch, NumPy, and any other libraries for data handling and visualization. 3. Data preparation. Collect and pre-process text data. This involves tokenization, cleaning, and creating a dataset suitable for training. Define a vocabulary and convert text into token IDs. 4. Model implementation. Implement the transformer decoder architecture, which includes building layers for multi-head self-attention, feed-forward networks, and layer normalization. Create a GPT model class that utilizes these layers. 5. Training the model. Define a loss function, example cross-entropy loss, and an optimizer, example atom. Set up a training loop that includes forward propagation, loss calculation, and back propagation. 6. Generating text. Implement a method to generate text based on a prompt using the trained model. 7. Fine-tuning and evaluation. Fine-tune the model on specific tasks or datasets and evaluate its performance. Step 1. Understanding the transformer architecture. The transformer architecture introduced in the paper Attention is All You Need by Vaswani et al. Is foundational for GPT. Key components include: self-attention, allows the model to weigh the importance of different words in a sentence. Positional encoding, since transformers do not have a built-in notion of word order, positional encoding is added to give the model information about the position of words in a sequence. Feed-forward neural networks, each attention output is passed through a feed-forward network. Layer normalization, applied to stabilize and speed up training. Step 2, setting up the environment. Make sure you have Python and PyTorch installed. You can install the necessary libraries using pip, bash, pip install torch numpy. Step 3, data preparation. For this example, let's use a simple text dataset. We'll tokenize the text and prepare it for training. Python. Import numpy as np. From collections import counter. Import torch. Sample text data. Text equals hello world. This is a simple example of GPT. GPT generates text. Tokenization. Tokens equals text.lower.split, simple with e-space tokenization. Create a vocabulary. Vocab equals counter, tokens. Vocab underscore size equals len, vocab. Create a mapping from token to index. Token underscore to underscore idx equals token, idx for idx, token, underscore, in enumerate, vocab.items. idx underscore to underscore token equals idx, token for token, idx in token underscore to underscore idx.items. Convert tokens to indices. Encoded underscore text equals token underscore to underscore idx token for token in tokens. Print, f encoded text, encoded_text. Step 4, Model Implementation. Here, we will implement a simple version of the GPT model. Python. Import torch.nn as nn. Import torch.nn.functional as f. Class GPT, nn.module. Def___init__, self, vocab_size, embed_size, number_heads, number_layers. Super, GPT, self, .__init__. Self.embedding equals nn.embedding, vocab_size, embed_size. Self.positional_encoding equals nn.parameter, torch.zeros, 1, 100, embed_size, assume max length of 100. Self.transformer_blocks equals nn.module list. nn.transformer decoder layer, d_model equals embed_size, nhead equals number_heads. For _in range, number_layers. Self.fc_out equals nn.linear, embed_size, vocab_size. Def forward, self, x. Sec_length equals x.size, 1. X equals self.embedding, x, plus self.positional_encoding : sec_length, smiley face, for layer in self.transformer_blocks. X equals layer, x. Return self.fc_out, x. Initialize model parameters. Vocab_size equals len, token_to_idx. Embed_size equals 64 size of the embedding vector. Number_heads equals 8 number of attention heads. Number_layers equals 6 number of transformer layers. Model equals GPT, vocab_size, embed_size, number_heads, number_layers. Step 5, Training the model. Training involves defining the loss function and optimizer, then iterating through the data set. Python. Hyperparameters. Number_epochs equals 10. Learning_rate equals 0.001. Batch_size equals 2. Define loss function and optimizer. Criterion equals nn.cross entropy loss. Optimizer equals torch.optim.atom, model.parameters, lr equals learning_rate. Sample training loop. For epoch in range, number_epochs. Model.train. Optimizer.0_grad. Create batches, for simplicity, using single sample here. Input_tensor equals torch.tensor, encoded_text, unsqueeze, 0, 1, sec_length. Target_tensor equals torch.tensor, encoded_text 1 plus token_to_idx eos, unsqueeze, 0, shifted input. Output equals model, input_tensor. Loss equals criterion, output.view, -1, vocab_size, target_tensor.view, -1. Loss.backward. Optimizer.step. Print, f epoch plus 1 / number_epochs, loss.item. Summary. In this first part of the tutorial, we outline the high-level steps for building a GPT-like model from scratch. We covered the basics of the transformer architecture, set up the environment, prepared the data, implemented a simplified GPT model, and started the training process. In the next part, we will cover text generation and evaluation techniques, along with more advanced training strategies. Note: This tutorial is an overly simplified version of what goes into creating a production-level GPT model. In practice, models like GPT-3 are trained on massive datasets with advanced techniques and considerable computational resources.